last week we were left at derivation of small signal model for MOSFETs. So as you remember, we drive the impedance or small signal resistance for the diode. So when we did that, if you recall, we found the small signal resistance, N is usually 1, Vt over ID, right? The terminal voltage divided by the current on the diode. And how we did it was we derived the formula. This was the current. And when we take the derivative of that with respect to the voltage, we find the 1 over resistance. We find the slope, and then reversing that gives you the resistance. So if you look at the MOS, and if you want to drive the small signal model, we did the similar thing. Where is it? And the current is basically a function of VGS and VDS. Why? In saturation, if you look at the formula, it is this one. The current is this over 2 times VGS minus VT, which is overdrive voltage, square, times 1 plus alpha VDS. So the first term is the actual formula. When we add the plus, this term is due to the early voltage effects, are like basically the VDS. If we draw the MOS, it is instead of this, it is this, right? So, and the x-axis is VDS and y-axis is IDS. So why this was happening, this channel modulation? Because if you look at back to the physics, we had a channel that's a length of L. And the electrons move this way. There is a source, there is a drain here. Drain is positive voltage, attracting the electrons. And we had a gate here. Like this is the silicon oxide insulator. And we have this metal here, just like we have the metal for the source, we have the metal for the drain. Okay. So this one, this gate, just like a capacitor, when it is above thresholds, it was creating a depletion region, right? And then this was the godfather that turns on the MOS or turns off the MOS. Okay, if it is bigger, it turns on. If it is smaller, it turns off. The VD is the other father, like it pulls the electrons and it creates currents through in that depletion region. And when this depletion, when this VDS actually, because there is a source here which is also in effect, when VDS is smaller than VGS minus VT, which region are we at?
Pitching, yani
we are at triode region, right? VDS is smaller than VGS minus VT. That means your current change. This is not the formula. There is a formula for that. Okay. And if VDS gets bigger than VGS minus VT, then what happens is now your pitch point starts to change. Pitch point is where this, electrons start to end accumulating. So normally, for instance, it was like this. Then we increase VD, became like this. Then it starts like that, and so on. And when it becomes changing its pitch points, for instance, if we find it at this point, let's say, what happens is actually the channel, the effective channel becomes this rather than the entire channel. And you call it delta L over L alpha. So, and this change in the channel is basically how you show that change in the current, because now your L, the formula was width over length, right? So now your length, instead of that, this one, is now it is this one. So your length becomes smaller, which means the current increases. So this one basically showing that when effective L decreases, your current increases as a function of VDS. And I explained several times why this channel gets smaller. You should look at the previous lectures. It will take another 5 minutes, so I'm not explaining again. So, this basically, this voltage, this node where it pinches, it has this VGS minus VT voltage. So when you keep increasing VD, you are pushing that voltage to the left side. So if that voltage VGS minus VT, let's say 1 volt, when VDS is 1 volt, you are right at the pitch. You are right by here. But if you make VD as, let's say this is 2 volts, that 1 volt now has to be here. This VGS minus VT, okay? So you are pushing that pinch point to the left. If this is 3 volts, then you're pushing this to here, that 1 volt. Okay. And the reason that pinch point is VGS minus VT is because we explained if this is gate, you are applying a VG voltage here, and that whatever voltage here, the difference between gate and this voltage should be VT to create some electrons. So if I have here pinch point VGS minus VT, let's say source is 0, so I am always writing VG. So if this is voltage VGS minus VT, as you can see, the difference between these two voltages is VT. VGS minus VT is VT, right? That's what you need to create electrons here. So that's why always this pinch point, wherever it is pinching, it is VGS minus VT, okay? So that was a recap, what we studied. Going back to the slides, now to create the small signal, you take the derivative of the current with respect to whatever changing the current. So VGS, VDS. So that means you have to take partial derivative. You take the derivative with respect to VGS times VGS. You take the derivative with respect to VDS times with small signal VDS. So when you do that, you create this formula, and you can see that ID is dependent to trans conductance, GM, and R0 resistance. And now from this, we can define the small signal model. And you need to know that this GM and R0, they are functions of bias current and bias voltage, okay, as well as length. So the small signal parameters are always parameters of DC points, okay? So now we define the small signal because the current is GM VGS, this ID current, plus VDS R0. we can define the first term like that and the second term like this. So the gate current is 0 because the MOSFET is like a cap. It doesn't have any DC currents because just like cap doesn't really in steady state, it's open circuit, right? There is no DC current through the cap in a steady state circuit. So similarly, MOSFET, the gate is a cap. So, and it won't have any DC currents. So drawing this small signal model, we can see that we define already these GMs and R0, and we can see that this is the most basic small signal model that defines a transistor, MOSFET transistor. Gate is here, drain is here, and source is here. So as you can see, gate doesn't have any currents. The VGS voltage is here. GM VGS is the currents that goes through here, as well as VDS R0. So we can basically model this resistor, the channel resistor, as R0. So VDS over R0 is another term that adds to the ID. So total current ID is this current, okay? So for the Pmos, the model is very identical. It's just you are supposed to study Pmos yourself first because I don't have time to cover this in this class. But everything is same, but it's just the formulas replace VGS minus VT with VSG minus VTP. So basically, you care instead of VGS, you care about VSG. Instead of the threshold voltage minus threshold voltage, you care about minus absolute threshold voltage for the Pmos. So you need to just go to the Wikipedia and write Pmos, okay, and then study. So this is just showing a slide for the Pmos, and you can look at it because for the Pmos, the current flows to the drain. So these numbers, parameters are same, but now what matters is, when there's a gate here, when there's a source here, when there's a drain here, the drain current doesn't flow this way, but it flows this way. So that's why, for instance, GMVSG is now flowing this way. S should be bigger than the gate, so we care about VSG and so on, okay? So when we look at the voltage amplifiers, we already defined these parameters before. There is input resistance, there is output resistance, and there is the gain, open loop gain with no load, okay? Same with the transistor amplifiers. So we were always looking at the op-amp like a black box. We were not really looking at the inside. We were only saying, hey, it is a R in, right? It has this, and it has that. So now we will start to get in the op-amp, and we will start to see what actually these different amplifier configurations are, okay? But it's important to know that how we find input resistance, how we find output resistance, how we find open loop gain, it's important, okay? So when you are given a circuit, let's say the most basic is this, just like this one, okay? You are connected to a signal. Signal has a voltage source, a voltage source resistance, we call it R signal, and output you connected to a load. So when I ask you, hey, what is the gain of this system? You are supposed to tell me the gain is V out over Vs. So, and you can divide V out over Vs into two parts. You can divide it into V in over Vs and V out over V in. So what does it mean? V in over Vs times V out over V in will give you V out over Vs, right? But it's easier to find these two terms. So let's first do that. V in over Vs, this voltage divided by this voltage. Well, it's just a simple resistive divider, right? So Rin divided by Rin plus R signal gives you V in divided by Vs. So this is check. How about V out over V in? So V out over, well, it keeps saying V in. So this is V in, okay? So it is the open loop voltage times a resistive division again. So this one V out and this one is V in. So here you have the voltage controlled voltage source, and this one voltage controlled voltage source goes through a gain resistive division. So the gain becomes this one, right? Because V0 equals AV0 times V in times RL over RL plus R0. Okay. So when you multiply these two, then you get the gain. So this is also called, you know, the DC gain of the circuit. So you can have different stages cascaded. Basically, you can have stage 1, you can have a stage 2, you can have a stage 3, you know. So I'm drawing like op-amp, but it's like an amplifier. So in the op-amp, actually, you know, you used to, well, it's same actually. In the op-amp, you also have that one. So when you cascade these three amplifiers, for instance, you just do the same thing, AV1, AV2, AV3, right? But you also need to just care about this resistor and this resistor. So you have to do the resistive division, just like we did in the previous lecture. So it actually looks complicated, but it's not at all. You just do a bunch of derivations, not derivations, you just do a bunch of multiplications, you know, to find the gain, okay? So now we learned what a MOSFET is. We need to show you how you actually drive the small signal characteristic. But before that, let's do a quick recap. So instead of writing, you know, like GMVGS, you can also write in BJT, you can also write different terms. But overall, the small signal model of this transistor, MOSFET or BJT, it is the same logic, okay? For the BJT, for instance, you have a base here, you have a collector, you have an emitter, right? So the names will just replace. The gate will be base, the source will be emitter, the drain will be collector, and the logic will be the same. So now again, focusing on the MOSFET, this is called P-type. P-type small signal. And there is also another type that you can draw the small signal, and that's called T-type. So we are right now focusing only the P-type, but if I have time, I will explain the T-type. And quick recap, the gate current is 0. The MOSFET is in saturation, so this is the formula. And from this formula, you can find the GM. And it's good that you first derive these things, and then you can memorize it if you like, or you can put it in your notes. And GM, I can tell you, hey, we are keeping the current same, but we are changing the voltage, input voltage. How does GM change, for instance? Or I can tell you, hey, we are changing the width and we are keeping the current same, okay? So basically you need to put it in the right formula and find how GM changes, okay? So the GM is a function of DC values, the currents, the voltage, and also the width over length. So the output resistance is the resistance that we see looking from the drain to the circuit. So when we do that, it's actually, you have to, just like, you know, in P-Spice, you connect the test source here, right? And then you look at the current and you divide the voltage to the current. It's the same logic, actually. Think it like this, like a twinning. So think like that you are finding the twinning voltage and twinning resistance. Same logic, you are finding the output resistance. And when you find the output resistance, it is actually this R0 is your output resistance here. Because this GMVGS, although it's dependent source, when you do the derivations, you see that the main factor is R0 here. So R0 is the output resistance. And you can also write it in terms of this early voltage effects, the channel modulation effect. Okay. And for a very basic MOSFET, let's calculate the amplification factors. Well, so this is our input, VGS. I'm not considering the input resistance and stuff, just this MOSFET. So this is the input, so this is the output. So input times GM is GM-VGS. This GM-VGS minus GM-VGS is this one, and it goes through, doesn't go through this one because there is no return path. So this GM-VGS goes through here, multiplied with R0, and GM-VGS R0 minus actually GM-VGS R0 becomes your output and output voltage. And when we divide this to VGS, the VGS cancels. So GM R0 is minus, but we are looking at the magnitudes. The GM R0 becomes the amplification factor when there is no load. Okay, we are not connecting any resistance here or any load here. So as you can see, this GM R0 becomes the amplification factor for a MOSFET transistor. And this is an important parameter because when technology scales, we usually care about these factors. How good a transistor can amplify, it's a good parameter for that performance indicator. GM shows you how good amplification it provides, and R0, how big its intrinsic resistance. This R0 is intrinsic resistance of the CMOS. Okay, It's basically like this resistance, the channel resistance of that MOSFET. But when we connect the load here in parallel, now the R0, it's big or not, doesn't really matter that much. I mean, it matters, but if we connect a small resistance here, let's say 5 ohm, this R0 won't really have any effect because 5 ohm parallel with a big R0, let's say 100 ohms or 1000 ohms, 5 parallel 1000 becomes 4.99, right? So that's why we need to look at actually the amplification factor without any loads connected. This R0 becomes important at some point because the reason it becomes important, not just for this amplification, because as I showed you, if I connect a 5 ohm, well, R0 loses any effect. But it is important because the output resistance, as you can see, is also R0. So when you connect a CMOS here to another circuit, this R0 will be your Thevenin. Or, for instance, we connect the resistance here. Now this Thevenin resistance will be R0 times, 1/1 plus GMR5. How do you know? I know it from my experience. You need to basically derive this like a nodal analysis and so on. But that's why this R0 is important, because it kind of defines your output resistance as well. So let's go to the next slide. So there is this body. Now we are introducing another terminal called body terminal. And this body is connected, so this is the source, this is the drain, this is the gate. So the body is connected to the body of the CMOS. So it's connected to another location in the 3D of the CMOS. And the body actually affects your circuits. So if you look at the CMOS physics, these were NPNs. And the body creates another substrate. And this substrate basically defines the flow of your current. So not going into so much detail, to understand how much something is affecting us, we always need to take its derivative. We always need to find its small signal parameters. So to find GMB, how that, just like we found GM, to find how the base affecting us, we call it GMB. Well, we need to take the derivative of the current with respect to that body voltage, right? So I call it BS because the body usually interact with the source. So doing that, when we do the derivative, we divide it into two parts because these can cancel, but it's good to divide it because we can easily write these ones. And anyways, now we have this function, GM times backgate transconductance parameter. And now this is another parameter that defines our current flow. So we already introduced this. Now you are introduced with this another current source that is defined by your body, okay? Usually in the questions, I will ignore this because, the purpose is not making it complicated, but just know that in the small signal parameters, we always have another junction. It's called body, and that affects your small signal model, okay? So basically this body creates a reverse bias diode and so on. So that's how it affects your small signal model. So for the Pmos, as I mentioned, the small signal is the same because the logic is the same. But as you can see, this is a Pmos, and what you care is this gate source voltage. The current is flowing this way, and the locations of the pins are actually interchange. Like what I mean with interchange, in an NMOS, you care about VGS minus VT. In a PMOS, you care about VSG minus VT PMOS, okay? So for instance, in an NMOS, VGS is 2 volts. Let's say VT is 1 volt. Okay, and let's say VDS is 3 volts. So VDS is bigger than VGS minus VT. That makes your NMOS in saturation. Similarly, in PMOS, your VSG can be 2 volts. Your threshold voltage is always minus, as the physics of PMOS tell you so. So let's say it's minus 1. So 2 minus 1 is 1 volt. But now, instead of looking VDS, you need to check if it is smaller or bigger than VSD, okay? Basically, these polarities are getting reversed. Instead of VGS, you are looking at VSG. Instead of VDS, you are looking at VSD, okay? I won't be asking this in the exam either, and I'm expecting you to learn it yourself, what Pmos devices, how it works similar to the NMOS, but in the NMOS it was NPN, right? In the Pmos it is PNP. Okay. So there is also like another hidden substrate here. So going to the next slide, let's look at a common source amplifier. So a common source amplifier means the common, whenever you say common, think it like it is grounded. I'm sorry, it's not grounded. Think it like it is, how can I explain? Common, for instance, yeah, think it like you want to ground it. So the node that you want to get is, for instance, this is a common source amplifier. So this is source, this is drain, this is gate. And with a MOSFET, you can create 3 different amplifiers, which means you can get a signal from some points. And let's say, for instance, here I can explain nicely. Okay. So there are 3 different configurations. There is common source, there is common gate, and there's common drain. So common source means you put an AC signal into the gate and you get the output from the drain. Common gate means you place a source like AC signal to the source and you get the signal from the drain. And common drain means you get a signal at the input and you get a signal at the source, okay? So whatever basically telling you the common source or common gate or the common drain, that is the name shows you you are not getting signal at that port. You are actually AC grounding that port. Like, what does AC ground means? So let's go first explain your AC ground. But before doing that, so I want to highlight this again. A common source means source is grounded. A common gate means you have a DC signal here, but it's not AC. So in the small signal, DC gets shorted. Okay? We are looking at the AC domain. You don't really care about DC signal. So common gate is shorted. Common drain, drain, you might have a supply voltage, but you don't really care about the DC signal. So this is shorted. Okay? So that's how the name convention comes from. Okay? So you can tell me, hey, if you are shorting it, how are we getting signal? How are we amplifying? Well, so again, you have two domains. One of them is AC domain, and the other one is DC domain. Let's figure out what is DC and what is AC equivalents of the circuits. So just looking at basic, let's say, Cmos or Bjt amplifiers. So you are given a configuration that is complicated, that you don't really know what it is, how you need to solve the circuits. So for instance, let's just look at this amplifier. You have a cap, you don't know why it is there. You have some resistance here, and there's another resistance here. There's another cap. There's a resistance here. There's a cap here, a voltage, a load here, a resistance here. So this is a basic one-stage common emitter amplifier. So now let's figure out how we can analyze this. Okay. So first thing first, we look at the DC voltage. There is a cap here at DC, basically, which means steady state eventually, because it settles quickly. The cap gets a voltage on it, so it becomes an open circuit. And the reason there is a cap here, we don't want the DC signal go into this way. Okay, we want to capture it because we want to put a bias for this transistor. So we want to separate this AC signal from the DC signal, and that is called a DC prevention cap, or it's called like a coupling or bypass cap. Okay, so going back to the circuits, as you can see, the C1 and C2 are DC blocking caps. So C1 blocks this DC voltage, which is this is 12 volt. So 12 volt is divided between this and this resistance. It's like a resistive divider. So you get a voltage here, which is 12 divided by 40 times 10. So it is 3 volts. Because the current going into this node is so small, I basically neglected. And this 3 volt doesn't go through the inputs. If we didn't put this, we wouldn't be able to make this 3 volts, right? It would become much more complicated. So we put a cap here. Similarly, we want at the output, we don't want this DC voltage to interfere with this output DC voltage. Then we can put a cap here as well. So they are called DC blocking caps. And if we, normally we can design it really big, like so it's big because at omega or frequency going to, like high frequency, they are already shorted. So AC signal will go through. So if this is big, you don't really need to do this. like at your design frequency, let's say your design frequency is 2 gigahertz, these caps should be short. That's what I care, because I want those caps not affect my AC paths. Okay, since their impedance is 1 over j omega c, at my design frequency omega, I want this impedance so low such that it's short. But I want, it's not easy to put big capacitances in actually RF microelectronics. In the discrete amplification, yeah, you can do that. But in the like actual RF microelectronics where you put, where you design the chips, it's not really easy to design these caps so big because they create their own resonant frequency and so on. They have their intrinsic parasitics. But that's another problem. So now we know what these caps do. And there is this C3 also, and C3 is a bypass cap. And the purpose of a bypass cap is to provide a low impedance path. What does that mean? So if I don't put this cap here, this VE will only see this 1.5 kilo ohm, okay? And you'll see that this amplification, this one-stage amplifier will not have so much gain because this, and will not have so much swing because this resistance will kill your gain. You'll see how in the later lectures or later slides. But I need to get rid of it in AC domain. Yeah, I can put it in DC domain, but in AC domain, in the domain where I want to get amplification, I want to put this cap so that at your design frequency, it becomes actually a short parallel with the resistance is short, right? So that your circuit actually becomes this. And this one is called, that's why, a bypass, signal bypass resistance. It goes to the cap. So it creates a low impedance path. So it removes the effect of RE, okay? And when we do the AC domain, we ground all the DC signals. Basically, we have a VCC here, we make that ground, okay? Ground is already ground. If you have a current source, just like you do the twinning, like when you find the equivalent resistance, you kill the current source, right? You make it open. It's the same logic. You short the DC independent voltage source, and you short you open the DC current source. So here is a good recipe for that. I will upload this. So for DC analysis, you just find the DC voltages, okay? And at DC, the caps are open. Inductors, if there are any, they are short, right? Because DC means omega 0. So the inductors are short, the capacitances are open. Open means high impedance. 1 over j omega c goes to infinite. So it means open, okay? J omega L goes to 0. So it's short circuits. So then doing that, just looking at the DC, you find the operating condition, Q point. That's called quiescence point, DC operating conditions. Now, because you got the DC, well, basically now, as I mentioned, the transistors, they need DC to have their GM, to have their R0, have a meaning, right? Now you found the DC, as I mentioned, now we do the AC analysis. You find the AC equivalent circuit by replacing all capacitors by short circuits. Well, this is not exactly right. Why it is not right? Well, the capacitors, this is the capacitor impedance. So it's saying that capacitors by short circuit, assuming that the capacitors are big. Okay. When you design a circuit, actually, whatever the capacitance impedance is and whatever your frequency is, that's your impedance for the capacitance. But here, for simplification, that's how the class is taught. These capacitances are taught to be very big. Because they are very big, this impedance goes to 0, right? That's why it's saying that capacitances are short. Because if the C is big, this impedance is basically short, right? If the L is big, this J omega L is so huge so that it says inductors by open circuits. So, for instance, if I draw here instead of the resistor, if I draw here an inductor, and if I draw here a cap, when you draw the AC, what you do is, these are called choke, C-H-O-K. That inductor, if it is so big, is called choke inductor. Because it's so big, it doesn't let any AC signal go through, because J omega L is huge, right? L is huge. That means whatever the frequency is, J omega L is so big. That means AC won't go through, but at DC, this is J omega L, omega 0, AC will go through. So that means you can short this for DC. And this is 1 over J omega C, right? Then you can basically open this, because omega is 0, this is infinite. So you can open this, and that will be your DC analysis. So now I told you a bunch of different stuff. It became a little complicated. Now let's look at the circuit again, and let's draw AC and DC together. So let's first draw DC. This cap is closed, like DC. This cap is like also closed, open. And this cap is also open, because everything is 1 over J omega C. So DC, this is your circuit. As simple as this. You find the voltage here. This voltage basically is VB voltage. And then you find this current. And this current is found with, two equations. You have to do an analysis here, because this VB, there is a VB voltage minus VBE. Now we are here at this point, VB minus VBE minus I emitter divided by R4 equals to 0. Okay. And the other one is 12 volt minus RC IC minus VCE minus IER4 is 0. Are you guys following this? So we basically have two equations, two DC equations that will help you find currents of the transistor. If you find IE or IC, they are related to each other with beta. So as you remember, IE will be IC plus I beta. I base, I'm sorry, not I beta. And I base is actually IC over beta. Okay, so you can write IE in terms of IC, right? Because basically when you look at the transistors, this current plus this current is this current. So you can look at this in the notes. There is this part called Bjt biasing, and it explains how you bias a Bjt. But simply, you have two equations and you can solve the currents of this Bjt. Now let's look at AC domain. We found the DC, so we can find all the parameters for a Bjt. It is Gm, R pi. You'll tell what's R pi. I'll tell you, and R0. And for the MOS, it's similar. There is no R pi, but there is Gm and R0, for instance. So AC domain, let's look at it. So now there is this cap, and the cap has the same 1 over j omega c. And because that cap is so big and omega is not 0, so omega is any AC frequency, it's 1 over j omega c is 0 because the cap is huge, it's big, but omega is not 0. So that makes this 0. So we can short this. And let's assume instead of this resistance, for simplification, is inductance. Okay, so, and in AC, this is j omega L, and omega is not 0, but L is huge. So this is a big impedance. So that means this is open, for instance. Okay. Because you don't really need a DC voltage, you are just looking at the AC analysis. So now your circuit becomes much simpler. You have a source here. You have, it goes to the base of the transistors. So, this is also short, like other caps. So if we draw the circuit, you have the signal here. It goes to the Bjt. There's a resistance here, and it goes short. Okay. And because the impedances here, the resistances here are so big, the AC signal will not even want to go there, because the resistance that it sees here, it will be much smaller. So we don't really care about these resistances here right now either. Okay. So going to the here, just it will summarize what I explained again, so that it's, these are new stuff, so you will understand it. So DC equivalent, you don't really care about your AC signal, okay? Because this is 1 over j omega c, the cap will be open, disconnected. So you disconnect this, you disconnect this. So your system becomes just this one. You find the operating conditions. Okay. And AC domain. So it just showed it already here. Caps become shorted. So this is shorted, right? There was a cap here, it becomes shorted. So this gets connected. This voltage source here, now it does it without inductance. It does it with the resistance. So whatever DC voltage source you see ground, you short it to the ground. So as you can see, this node, it has a resistance R2. It has a resistance R1. They are connected to the ground. But because they are big, we don't really care that much about them. And if we have a node, we have a huge resistance. It's just like open. But it matters if this resistance is small. It's like shorting it. Okay, same logic. So then this 22K at the output is you short all the DC voltages, right? So these resistance become shorted to the ground, as you can see here. At the output, you know, this node, there is RC short to the ground. It's not shorted, but basically this RC connected between this node and the ground. So then R3, again, from this node, is connected to the ground. These resistance R1, R2 from this node, they are connected to the ground. Okay, so now this is your small signal model. This cap, because the impedance was 1 over j omega c, right? Same logic with the other caps. The cap is so big and frequency is not 0, so this goes to 0. So you lose this RE in the AC. There is no RE, as you can see. Okay? So now the circuit is this. What you need to do, you gotta draw the small signal equivalent of this transistor. First, you can simplify the circuit. These resistors are in parallel. So this one becomes parallel 104K, equivalent of these. These become in parallel. You can find the equivalent resistance. So now this becomes your circuit. And the next thing will be drawing the AC equivalent. Let's see if it does that. So this is again doing this for a MOSFET, same logic. And as you can see here, it put a choke here. That in the actual systems we usually put a inductance here. It's not a big inductance. We put a cap and we make these L and C, we make sure that they resonate instead of putting a very high inductance. Okay. So you want this node to be high impedance. If you make this high impedance, any current coming into this node, it will create a big voltage, right? Because current times this impedance becomes voltage. So this node should be connected to a high impedance circuit system. So because current times this impedance is voltage, and you want voltage to be at the output. So if I just put a small resistance here, short to the ground, you will kill all the voltage, right? Because all the current will flow this resistance. So that's basically something that you don't want. That's why, you know, here the most basic thing is putting a choke here so that this sees the infinite impedance here. Okay? And it just goes to the load directly. This is all new stuff for you, so you should definitely study. And for the Bjt, the logic is same for the small signals. But in CMOS, you didn't have a resistance.
Now in Bjt you have a resistance called R pi, and R pi is input resistance for the Bjt, and it is equal to B0 over Gm. So B0 was the current multiplication factor, right? I beta times beta was IC. This beta comes from Bjt physics. You know, if the recombination, those electrons and holes, it's a function of that recombination. And if the beta is big, that means the amplification factor is big, right? We want beta to be big because we want to get a much higher IC. So instead of GMVB, you can write here beta IB. Same logic. So beta IB means you have an IB current, small signal. So you are multiplying it with beta, right? So you have a small signal IB. When you multiply it with beta, you have the small signal IC here. Or, as it does here, GMVBE. You have a small signal VBE voltage, and GM is the trans conductance. What is trans conductance? Current divided by voltage. So here in this case, IC divided by VBE, small signal. So we call that term trans conductance GM. So instead of beta IB, you can similarly write GMVB. We usually exchange this. Either of them you can use it. So as you can see, the small signal is very like to the MOS. The difference here is R pi. In the future, you'll see much more complicated terms coming into the effect. So you will see a C between here. And now the system, the circuit becomes much more complicated. Why? Because this is your input, this is your output, right? For a common emitter amplifier, where you apply the signal here and where you get the output at the collector, let's say. So now the base and the collector are just connected with a cap. So this cap is an intrinsic cap, and it comes into effect when omega goes high frequencies. Why? Because, you know, when omega goes high frequencies, the impedance of the cap is 1 over j omega c, right? Now this cap becomes small impedance. So when it gets shorted, well, you don't really have any gain. Whatever you have a voltage swing here at the base, a signal, you see that the collector. So your amplification is gone. So this cap comes with the transistor. So if you make this transistor big, if you increase its, you know, dimensions, this parasitic cap also goes high. And when this parasitic cap goes high, this impedance gets small, right? So then you're in trouble. So that shows you that you cannot increase this transistor's dimensions as much as you want. You are limited by parasitics, you know, because the cap comes, you know, with these dimensions of this Bjt. So if you increase this transistor so much to increase the gain, GM, or to increase the IC, or whatever, then you think that your amplification will go high because you are increasing GM. You think that GM will increase the current. Well, yeah, it will increase the current, but now you are shorting base to collector slowly, right, through this cap. Similarly, you have another cap here and stuff. So I don't want to make it more complicated. It's already complicated. So right now you are only supposed to know the small signal pi model, hybrid pi for a BJT, for a Cmos. And you are supposed to know what the transconductance is, how you calculate R pi, how you calculate R0 for a BJT and Cmos. Okay? What time is it? 4:25. Okay, let's do a few more slides, then take a break. So, and similar to the CMOS, in the BJT there is PNP, right? In the MOSFET there is NMOS and PMOS. In the BJT there is NPN and there is PNP, and the logic is same. The small signal is same, but the polarities change. So instead of VBE, you care about VEB voltage, for instance, and so on. So, okay. Okay, so let's look at this transistor. We already explained you how you can do AC and DC equivalent of the circuit. And we were here, we did the AC domain. And first we did the DC domain, we found the Q points. And then you did the AC domain, you found this circuit. And now what you need to do is you gotta put the transistor model into the circuit to solve the circuit. Just like this. Okay. So the circuit was there and you put this one into this transistor, right? As you can see here at the Q, you just put that here. Okay. Any questions so far? Basically, you are putting this Q, you are putting it there, and it becomes, okay? Now, you should show your nodal analysis skills. It's just a circuit you already learned how to solve. There are a bunch of parameters, there are a bunch of voltages, resistances, voltage dependent current source, and you just analyze the circuit and find input resistance, find output resistance, find voltage gain of the circuit. So why this is called, for instance, common emitter, I explained, right? Like I explained the emitter is grounded, while also emitter is common to both input and output signal. What does common mean? Like this emitter is basically like connected to both collector and both the base. But I think the way I explained makes more sense, and it's, I remember it always that way. So let's find the gain of this common emitter amplifier, for instance. Okay. So looking at the circuit, we simplify this RO, RC, R3 as R load. So we write it as R load. Okay. And here is your VBE voltage. It's actually where your transistor is here, right? This is base. This is emitter. This is collector. So this is where your transistor is. So, and now when you look at it, let's first calculate VC over VB. This is VC is minus GM, VBE over RL. This current is minus GM VBE. You multiply it with RL, and when you divide to the VB voltage, because emitter is ground, VB is cancelled, so you get minus GM RL. And you know the RL, so you found the gain of the circuit with respect to VB. But now you also, if you multiply this with VB times VB divided by V in, you should be able to find the entire gain of the circuit. What we found here is only the gain from collector to the base. But when I ask you, hey, what is the gain of the circuit, you actually find V out over V in. Okay? Here we only found V out over V base. Now you have to multiply this with V base divided by V in. So V base cancel so that you can find VC, which is V out in this case, divided by V in, right? So I'm sure you can solve these ones because if you are good at nodal analysis and stuff, but important thing is to know different amplifier types. And the purpose of this class is actually to show you different amplifiers. So this is a common emitter Bjt, like common, like when you hear the emitter, you will already know that it's Bjt because Cmos doesn't have emitter, right? So for Bjt, we have 3 different amplifiers. And for Cmos, we have 3 different amplifiers. So this is base, this is collector, this is emitter. And let me redraw the MOS somewhere, which is not really interfering. And for the CMOS, you have the gate. For an NMOS, you have the drain, you have the source. Okay. So you have three type of amplifiers for either circuit, and the logic is same. So one of them, as I mentioned a few slides ago, one of them is you apply an input signal, you look at the collector output. The other one, this is called common emitter. Okay. So whatever common, you don't get signal at that port. You get the signal from the other one. Okay. So here we apply a signal at the base, and you get the output at the collector. So this is common emitter. If we are applying a signal at the base, and now you are getting a signal at the emitter, okay? Now, what is this called?
Common collector.
Super. Common collector. And then we have another one, which we apply a signal at the emitter, and you are getting the signal at the collector. What is that one called?
Common base.
Common base. Because the base is not related. Your input is at the emitter, output is at the collector. So you write the base here, common base. Similarly, again, first one, common emitter. You apply the signal at the base, you get the signal at the collector. What is left? Emitter. Okay? So, common collector. You apply the signal at the base, you get the signal at the emitter. What is left? Collector. Okay? So whatever left remaining, that defines the name of your amplifier. So that's just how they did it in the literature. And now we'll get into the details of, digging into those amplifiers after a break. But first, let's look at the CMOS logic. Same logic. We send the signal to the gate, and we get a signal at the drain. So common name states. What is the name of this amplifier? Amplifying, sending a signal at the gate, output at the drain. What is left?
It's common source.
Common source. How do you know these ones? You just learn it here, or you just took the class before?
No, but I watched a video like
Oh.
yesterday about that. Yes.
Awesome. It's so cool. I hope all the friends will have a chance to do that. You apply a signal at the gate, and now let's say you get the signal at the source. What's left? Drain. So now let's say apply a signal, and you get the signal, you get the output at the drain. What is left? Gate, common gate. Okay? So common source, common drain, common gate. Three important one-stage, one-transistor amplifiers for the CMOS. For the BJT, common emitter, common collector, common base. And all of them have different characteristics. What does different characteristics mean? Well, we define three important things: R in, R out, and gain of that one-stage amplifier, AV. So, for instance, common emitters will have a high gain, and let's say it will have a low R in and high R out. Okay, but if you look at, let's say, common, for instance, common collectors, where you apply a signal and you get the signal at the emitters, well, the gain is 1. But why are we using it? Well, because we are using it because our out of this is not as high as, you know, the common emitters. So depending on your needs, you know, you select these amplifiers in your system. Okay? For instance, you have a block here, and you have another block here, and for instance, this R20 is so low. Well, you don't want to put a system that has a very big impedance here, R in, because then you won't be able to maximum power transfer, right? Because R20 is, let's just draw this equivalent. You have a voltage source, you have a R20, which is, let's say, 1 mega ohm, okay? And let's say you design an amplifier, but its input impedance is so low, 10 ohm. Well, you won't be able to get any power on this 10 ohm. Why? Because the most of the, you know, current, like voltage drop, will be on this 1 mega ohm. But instead of 10 ohm, if you have a high impedance R in, just like this one, 1 mega ohm, well, now you will have the maximum power transfer, right? So basically, your needs, you select the amplification. So now the design comes. You use to analyze this. You will learn how to analyze these circuits. But when the design time comes, because you analyze these circuits, you will know which one to use it in the system or in your circuit. Okay. So in the op-amp we always learned buffers, right? So actually this common collector amplifier is a buffer. The one I just wrote here with the gain of 1. Remember, we were doing this. So just same logic. The V in, this becomes V in, so V in becomes V out, right? So this is an amplifier with a feedback of 1. it's not the same logic, but you can use, instead of this, you can use a common collector because the gain is 1 and the output impedance is quite low, as you can see. So you can use this common collector as a buffer. Okay. So let's take a 5-minute break. Then I will explain you all these transistor types or all these one-stage amplifier types. As you can see, there are 3 different MOS transistor amplifiers: common source, common gate, common drain. So, and we'll dig into each of them one by one. So let's start with common source, where we apply input at the gate and we get the output at the drain. That's why it's called common source. Okay. So looking at the common source small signal circuit, I'm looking at the AC domain. We have the transistor connected to an input signal with a resistance R signal, and the RD and RL, becomes connected to the ground. And now you replace this transistor with a small signal model, and then you drive the circuit. You drive the R impedance, input impedance, you drive the output impedance, and you drive the gain. So doing that, so by finding the V out in terms of, for instance, VGS, we found this, I showed this in the previous slides. And then if we divide this to the input voltage, this is the gain of the circuit, V0 over Vin. Well, but as I mentioned, this is the Vin here. If you want to find it with respect to V signal, that's what we really care, then you have to do Vin over V signal as well. Okay? So it's important what the question or what whoever asking you is asking transfer function is. Is he asking or is she asking V out over V in or V out over V signal? Okay? And usually V out, V in or V signal. So usually what we care is V out over V signal, because when you connect a signal into the system, this is like a black box. You won't really be able to, solve the separately. Yeah, but it's not really black box. This is connected to, let's say, a source analyzer or a source generator, so that you won't be able to sometimes measure it directly, but the intrinsic gain is the gain of this transistor alone, which we multiply GM-VGS with R0, remember, and we found the gain GM-R0. But when you connect it to the outer circuit, to other elements, now other transistors come into effect, right? So you can simplify this as we did it. These are in parallel, so you can make that parallel, and you can simplify the circuit as much as you can, and you can find the other parameters. For instance, if I ask you what is the input impedance of this, well, there is no current getting into the circuit because this is in the small signal, this is open, and because there is no current, Vin divided by 0 current, input impedance is infinite, right? But you'll learn that in the actual CMOS, there will be a capacitance here. So it won't be as simple as you did it here. But for simplification, basic level, because we are looking at very low frequency right now. We are not considering the entire bandwidth. So this is like a low frequency analysis. And because we have a cap here at low frequency, it is open, right? So basically we are ignoring this cap. And so for now, this is a small signal model. And the input impedance is, as you can see, it's not connected, so it's infinite. So let's look at the output impedance. So now we are looking at the circuit from the output. And this is a load. We don't really care about the load resistance because we care about whatever is there other than the load. So we look at the output impedance. And when we do that, remember, it's just like finding the equivalent to an resistance. It's the same logic. Well, it's actually the same thing. When we were finding the RTH, that's exactly the same thing we are doing here right now. So we are shorting all the voltage source, independent voltage source. If there's a current source, we would leave it open. And we are not touching the sources. Okay? So looking at it, there is RD here, there is R0 here. So one impedance, and we need to know what is this impedance, looking from here to the left. And it will be parallel of those three impedances, right? Let's call it Rx. So the R out will be Rx parallel R out, like intrinsic output resistance, parallel RD. And now let's find Rx. To solve Rx, we need to find what is this current. To solve this current, we need to know what is GS. Well, the gate, this is grounded already. So there is no current. This is open. This is ground. There won't be any current here. Well, the gate will be 0 volts. Well, the source is 0 volts. That means VGS is 0 volts. If VGS is 0 volts, this current is 0. If the current is 0, that means it's open circuit. There is no current going there. Well, that means Rx is now infinite because the current going here is 0. So that makes Rx infinite. So if Rx is infinite, it has no effect in the circuit. So the output impedance is simply R out parallel RD. Do you have any questions here? Okay, really? Everybody understand this? Okay, well, so let's continue then. So if we connect the resistance at the source like this, now what happens? Well, same logic, we'll draw the circuit, we'll connect the small signal resistance of the amplifier, and we'll do again bunch of nodal analysis. The same thing applies for input resistance because this is open, input resistance is infinite. So let's look at R out. Or first, let's look at the gain. So to solve the gain of this circuit, you have to do some nodal voltage method. So you gotta do a nodal voltage analysis at Vs, and you gotta do another one at V0. And doing that, so you find V0 in terms of V in. And that means you can find the gain of the circuit. Okay? And as you can see, the gain is GM R0 times RD parallel RL divided by R0 plus 1 plus GRS plus RDRL. It's like a bunch of terms, but that simplifies. Why it becomes simplified? Because some of those terms are much bigger compared to other ones. For instance, if you look at this one, we take the R0 into parallel and stuff, then eventually these R0s cancel, so this becomes that. And then because R0 is RD is much smaller compared to RL, it says. So I don't know why it says that, but so RL goes away and now comes this. So whatever you are given in the circuit, you can do those assumptions. So for instance, if RD, R0 is huge, let's say 1 mega ohm, then basically this term will go to 0, right? And so on. You can make those calculation assumptions when you are solving it. Now, let's look at the output resistance of this. And let's do a test method. You connect the voltage source and you find the current, because it's not trivial as before. It was trivial before because there was no RS. Now we connect an RS and it becomes a little bit more complicated because this one is not VGS, it's not 0 anymore. G is, yeah, it is 0 volts, but source is not 0 volts. So this current doesn't become an open circuit. So now you have to find IX. So again, you do two voltage, two nodal analysis. One of them is at VS here. And then also, you know that VGS is, because gate is 0, you can write it as minus VS. And when you do that, you find a relationship between VS and VX. And what we are trying to find is VX over IX. Okay. And we write IX as I1 plus I2. And we write I1 plus I2 in terms of VS, VX. And then we replace this with that. And we write Vx in terms of Vs, and eventually Vx is, you know, Vs and Vx blah blah, they cancel. You write Ix in terms of Vx voltage, and eventually this is what we want to find. So when you divide Vx by Ix, you know, the Vx cancels, and you know, this becomes your R out. Okay, and this is not trivial to do it. You know, it is just like a question itself, but I'm just showing you how to drive it. Okay, so when you might be given a much interesting amplifier, and then you might have to drive how to calculate this output impedance. So basically, you learned this already in the Twenin method. This is your Twenin block, right? And you learned it already in 202. You learned it in this class again, how to solve that R2N. This R0 is just your R2N impedance. This one. Okay. So now let's look at the common gate. When it is common gate, what happens is you gotta solve the circuit again, but now where you apply the input, where you apply the output, they change, right? And because they change, you have to put the same small signal model in a different configuration. So the configuration now becomes this one. As you can see, you are applying the input at the emitter, not the emitter, sorry, at the source, and you are looking at the signal at the drain. So that's why we call it gate, because neither input or output is at the gate. So we are calling that as basically we are naming the amplifier. The node that is not getting actually used, that is grounded. Okay. So going to the circuit again, we apply the signal here, we get the output here. So what you do is you draw the small signal for this. You ground the gate. That's what we do. Because normally you have a bias voltage. But AC domain, in AC domain you have to short this, right? Because it's DC signal. So shorted. So it's shorted. And now your source is connected to your signal here. So you connect this one to your source, as you can see. And now you are doing the source drain, the same logic you do it. Okay, there is the drain, and then the rest of the circuits. And then we gotta solve the output impedance, input impedance, gain for the circuits. So to find the gain, you do again bunch of node voltages, and you find that gain is GM times R0 parallel RD, and then you find the input impedance, you find the output impedance, and so on. And similarly for the common drain, it's another amplifier. You apply the signal at the input, and you get the output at the source. So you apply at the gate. So that's why we call it common drain, right? The drain is the port that is grounded. Because normally there is a DC voltage here, whatever the source, whatever the voltage is actually supplying the circuit. But in AC domain, we ground it. Okay? So, and doing that, so now you are again putting the small signal into the circuit. The gate is connected to here, source again here, drain is here. Now the drain is connected to the ground, and the source is connected to your output. Okay? So you always draw the same small signal. This is called, as I mentioned before, pi hybrid model. Okay? Pi model. So there is also a T model, which I will probably put the notes, but they don't really use it that much, but sometimes it helps. Instead of this small signal, you can make another small signal configuration, which will help you solve the circuit. But mostly we use pi model. Anyways, for this configuration, again, we need to find AV0, the gain. Also, we need to find input resistance and output resistance. And you just do it so by the same ways I taught you. Similarly, for output resistance, you short your signal. So this one becomes shorted. And then you solve our output. Similarly, for Rin, this is not connected, so this is infinite, right? But if we look at the previous transistors, the common gate, Rin is not infinite, right? Because now Rin is connected to the source. Remember? So because for the common gate, this is the configuration, we are not connecting the source to the gate. We are connecting the source, the signal to the source. So your input is not infinite anymore. So when you do the small signal, you will see that your input impedance is this. And because R0 is big, this usually goes to 0. So your input impedance is 1 over GM. Okay? So why is it important? Because if you need a circuit that don't want an input impedance of infinite, but it might, maybe need an input impedance of very small, like 1/GM, like 50 ohm, then you would use that configuration. Yeah. And it's good to know all these common source, common gates, and common drain amplifiers. And common source, if we connect the resistance here, we call it common source with a input, with a source resistance. So these are the 4 fundamental configurations for the MOSFET. And probably I won't go through the same configurations for the Bjt, but it is entirely the same logic. You just replace this with the Bjt, and the entire logic is the same. What you need to know is for the Bjt and Cmos, there is this differentiation. What is the differentiation? Well, the differentiation is their DC parameters are different. What does DC parameters being different mean? Well, so when you do the small signal model, as you can see, if you compare them, there is this term called trans conductance. So for a bipolar transistor, it's IC over VT. For a MOSFET, it is this one, 2 times drain current divided by overdrive voltage. Or, you can write it this way as well. Or you can write it another way, as well, in terms of voltage and current. So, I'm sorry, voltage and Kn. So, you need to know these things by heart. All these open notes in the exam, eventually you can look at the notes as well, but you need to know what they mean, how you calculate them. So for a Bjt, the input impedance is R pi, but for a MOSFET, it's infinite. What does it mean? When we draw the small signal, we were drawing like this, right? So in the CMOS, this was open. But in the Bjt, we connect R pi resistance here. Okay? Because that R pi resistance, the reason that there's a resistance here, the Bjt has a different physics. So actually, the current is a function of this VBE voltage, and the R pi is actually this base emitter voltage times this IB current. And therefore, the current will create like voltage will create a current. Therefore, we have to define a R pi here. But you are welcome to go to the Bjt notes and understand, why there is this R pi here, and why do we define it as B0 over GM. And I will also notate in the elements where you can read those. And also output resistance, R0, this output resistance. In Bjt, we calculate it as VA over IC. And VA is the voltage actually that defines this early effect. And VA is this actually when you project this. I draw it really badly, sorry. So when you project this to the x-axis, this voltage is minus VA. So it kind of shows the slope. So if this VA is big, that means it is like that, right? Because the projection will be very high. So that means this slope will be small, and that means the resistance will be big because resistance is 1 over that slope, right? 1 over that slope. So that means if VA is big, R0 is big, right? Which also shows it here. So, and that is defining your output resistance R0 because this change is a function of how your characteristics change with that common emitter or in the Bjt or drain source voltage in the MOSFET. Okay? And in the MOSFET, it is this one, 1 over alpha over ID, 1 over alpha times ID. Alpha is the parameter that defines your channel length modulation. Just like the Bjt, you know, in the Cmos, you also have that same effect, right? So, and this effect is just like Cmos, but we don't define it VA due to the different physics. We define it with delta L, the effective length. And effective length is also a function of this alpha. So ignore this interesting voltage gain UF. You don't really need to know this. So a Bjt, the bias, the DC condition, we use this formula for, you know, for this region, and for the MOSFET, we use this formula for this region. For the region we want to amplify and where we want to use the transistor amplification. So we don't really use MOSFET triode region, or we don't really use this Bjt, this saturation region or linear region. I get confused sometimes. Or this region in the Bjt. We use this region for the Bjt and the Cmos. Okay? Because this is where your gain is constant, except that the non-ideal effect that your current goes slightly high, right? So that's called channel length modulation in the NMOS. That's called early effect in the Bjt. So this slide is a good slide. You know, try to understand this slide well. Also, here it compares a Bjt with a NMOS transistor. So how it makes the comparison is, well, so we have a common emitter and we have a common source. Common emitter is a Bjt amplifier, and the common source is a MOSFET amplifier. But logic is same. You apply a signal at the input, and you get the signal at the collector for the Bjt. And for the NMOS, you apply a signal at the gate, and you get the signal at the drain. Okay? And looking at these two amplifiers, when we compare them, it compares its terminal gain, rule of thumb estimate for GMRL, voltage gain, input resistance, output resistance, and makes a basic comparison. And it kind of shows you with a fixed DC bias, which is also your homework question, with the same bias of these transistors, which one will give you more gain. So, you know, which transistor would I use, you know, like spending same power consumption, because in the DC domain, these are connected to a voltage supply. Let's say they are both 5 volts, okay? And you have the same current source, same current, not through this Bjt. Let's say it is 1 milliamp, or, you know, yeah, let's just assume it's 1 milliamp. It might be different, of course. So now their power consumption, DC power consumption is same, 5 times 1 milliamp, voltage times current. That's your power consumption. That's how much power you are getting from your battery or whatever your supply. And this power consumption, you want to minimize it, right? Because you don't want your iPhone to die as quick as possible. You want it to stay. So you don't want to spend so much current, from a supply. Therefore, in an amplifier, we want to minimize this DC, VDC, IDC, and we want to maximize the amplification factor. Whatever the signal here, we want a very high swing signal at the output with a small current consumption. And that is called actually the trans conductance, right? As I described several times. It defines your current divided by your voltage in the AC domain. So how much swing you have here, how much current swing you are getting at the output. So as if you remember the small signals, when we draw it somewhere here, like for instance for a MOS, there is this GM-VGS here, right? That defines, hey, I have a VGS signal, a small signal, and the current I'm getting at the output is GM times that, which means you want a big GM. You want your current at the output be a big function of your input for a small DC consumption. Remember, GM is a function of DC parameters. Okay? DC defines your GM. So, but you need to figure out which one is more efficient compared to others, a Bjt or a Cmos. And actually, the answer is here, but you can do your Google search. Okay. So that's it for today. Do you have any questions? Most of you are probably sleeping right now. Okay.
Hocam son sorduğunuz soruda hangisi efficient derken common source ile common emitter'dan bahsetmiştiniz değil mi?
Evet.
Tamam.
Sanırım ödevdeki ikinci sorunuz buydu zaten değil mi? BJT'de common emitter homework for is asking if the BJT or common if BJT or MOS amplifier or like a common emitter or common source amplifier is more efficient, I think. If I'm not wrong. The first question is asking you how the Bjt current changes. Actually, let me open the homework page so that's a good. If you remember, the Bjt current is IS saturation current times exponential VBE over VT. And here there are different parameters that change with respect to temperature. But it's asking if GM changes. So when you have the GM, what is GM for the Bjt? It is this current IC over VT. Okay. So this bias current, let's say 5 milliamps, and VT is 25 millivolts. VT is KT over Q, right?
Yes.
So 5 divided by 25, 5 milli divided by 25 milli is 1 over 5. So now GM is 1 over 5. So it's asking you what happens when we increase the temperature from room temperature to, let's say, the Bjt became COVID. So its temperature increased. Okay? So now, well, Okay, that would be a good midterm question, a final question. So Bjt became COVID, and how does this GM change? Well, so the two things: how does the IC change, and how does VT change? Well, it's obvious. There's a T here inside VT, so VT goes up. But the question is, how does IC change? So in IC, there's IS, and inside IS, there's Ni square, free electron density. So free electron density increases with increasing temperature. But also there is this VT, which is this VT right here. And it also changes with temperature. So the question you need to Google, you need to search is how this current is changing with temperature. Because you know already the denominator increases, but the numerator, does it increase or decrease? Okay, that's what you need to figure out. And I am asking you not just tell me, hey, it increases or it decreases. I am asking you to find this equation and to draw it in MATLAB. Basically, I am asking you to define that equation, like write the formula in MATLAB, like code it, and in MATLAB you will get me a curve. This is the temperature, this is the GM. It might be this, it might be that, it might be this, okay? It might be that. So, and there is this thing called Shockley. How was it? Shockley equation. Something like this. You can Google this. Shockley, maybe something like that. So this is a physicist, the Shockley, and he, like back in the history, investigated this problem. Why? Well, why this is important? Well, it is very important because you might, in your iPhone, design a transceiver or design an amplifier that has BJTs, just like you learned a common, you apply the signal, a common emitter, you get the output at the collector. So let's say your antenna is connected to an amplifier, okay? There are, of course, a bunch of other blocks here. But now your signal comes here, it goes to the collector, amplified, goes out to the antenna. Well, this system, now you went to the Antarctica or you went to Arizona, cold or hot, some different weather. This amplifier will have a different characteristics, right? Because GM changes, which means your small signal model changes, not the model changes, but that parameter changes. And your amplification, this is your amplification factor. So instead of getting like 40 dB gain, in a hot temperature, are you getting 60 dB or are you getting 20 dB? And we don't want this change. We don't want 20 dB or 60 dB. Every temperature, we design our systems to have the same gain. So that's why RFIC is hard, because with different variations, you want a stable system. Okay? But the question is asking you, how does this GM change with different temperatures? Okay? It's a very fun question. The second question is asking you, efficiency matters. Using a CMOS transistor or a BJT, for instance, you can take the example of common collectors or CMOS common source. Input, you get the output. Input, you get the output. Just apply the same current, say 5 milliamps. Okay? Apply the current 5 milliamps. and then, find the GM similarly. Find which one will provide a higher GM. Of course, for that 5 milliamp, you need to find the VGS voltage here. And for that VGS voltage, you need to know the bit over length. And similarly for the BJT, this current is provided as, IS exponential EB exponential EVB over VT. So you need to know IS and stuff. But there's a rule of thumb, for similar sizes of transistors and stuff, you should basically Google it. Which one is more efficient? Okay? Like everything same, the current is same, the sizes are similar and stuff. Which one is which transistor gives you a higher gain, higher GM? Okay. Cool. Any more questions? Wow.
Hocam benim bir tane var.
Tabii.
MATLAB'de aslında bu statement'ları tam olarak çizmeden veya anlamadan önce PSpice'da da dediğiniz gibi çizebiliriz değil mi? Yani hani iki şey içinde, statement 1 ve 2 için.
Tabii. Zaten aynen. Yani hani ben söylemedim ama onu da yapmanızı bekliyordum. Yani
Tamam.
iyi oldu söylediğin. Yani artık PSpice gibi bir tool'u kullandınız. Hani benim size bunu kullanın ya da kullanmayın dememe gerek yok. Dolayısıyla elinizde artık bu sizin şeyinizde, cebinizde her zaman kullanabileceğiniz bir tool. Yani
Teşekkürler hocam.
kullanırsanız, rica ederim. Kullanırsanız kesinlikle yararlanırsınız. Hatta temperature modeling için bile PSpice kullanabilirsiniz. Transistörün içine girerseniz farklı temperature'larda transistörler farklı GM gösteriyor olabilir. Sonuçta o koyduğunuz library, the transistor models you get from the library, actually they are also temperature dependent, I believe. So if you want to get into more complicated stuff, you can look at how those transistors are modeled and stuff. But that will be a little much complicated for you, so up to you.